Hello, this is Dr. Joe Trout, and today we'll be speaking on the science of ice cream and units and conversions and terms, such terms as mass and weight and density and volume. So in physics, we have to talk about all kinds of different sizes and shapes. And for instance, the Bohr model of an atom, um, in which the electrons orbit a nucleus of protons and neutrons, has a size of about 1 times 10 to the minus 10 meters. We can actually see these things by using a scanning tunneling microscopes, and scientists can see the individual atoms that compose up the sheet of gold. We also have really large distances. So the distance from the Earth to the moon may seem really intense, but really it's just a tiny fraction of the distance from Earth to other celestial bodies, like our sun or the next distant star. If distances were given in some unknown unit, it would be maddening. So many of you probably are familiar with miles and feet and yards. And when you hear the terms like kilometers and kilograms, it gets a little confusing. So really, we have to worry about three fundamental dimensions. So there's length, time, and mass. And all the other dimensions can be derived from these. So in this class, we'll mostly use the meter, the second, and the kilogram. The first time the meter was defined, or in 1790, the meter was defined as 1/10,000,000th the distance from the equator to either pole. That might seem like a reasonable thing, but it's really hard to measure. Later, it became there is a platinum iridium rod that was kept in a special bolt with two scratch marks on it, and was how they defined the meter. More recently, we defined it with the wavelength of orange light, and now finally, the distance that light travels in some fraction of a second. In time, it used to be defined as 1/86,000th of a mean solar day. And, and now it's defined as the oscillations of a cesium atom. And for mass, until very recently, it was just a chunk of metal that they held in a special volt, and that defined what a mass was. So some of the history is in 1790, the length of the pendulum, it was defined as the length of the pendulum that swings at half of its maximum distance in 1 second. So the problem with this is that we had to define a second really well. And as I said, it was defined as 1/10,000,000th the distance from the North Pole to the equator. And then it was a length of brass rod, but they found that the brass rod would expand and contract due to temperature differences. So then they switched and it's a little soft. Then they switched to a platinum rod, and um, and it was stored in a vault. And then it was defined to be at 0 degrees, and then at some atmospheric pressure, right? So a normal atmospheric pressure. So this is a picture of an atomic clock, which uses the vibrations of a cesium atom to keep really precise time, better than a microsecond a year. And the fundamental unit of time, the second, is based on such clocks. And this image is looking down from the top of the atomic fountain nearly 30 feet tall. The meter is defined as the distance light travels in some fraction of a second. and distance traveled is speed multiplied by time. As I said, there's huge differences in the sizes we have to worry about in science. These are tiny photoplankton that swim along crystals of ice in the Antarctic Sea, and they range from a few micrometers to as much as 2 millimeters in length. Here's a picture of galaxies colliding 2.4 billion light years from Earth. Light year might sound like a unit of time, but it's actually a unit of distance. If you hear somebody talk about a light year, they're talking about the distance that light travels in a year. This is an old double pan mechanical balance. So what they used to have was, instead of electronic balances, they would have a lever and sets of weights, and you put your stuff in one pan, and then you keep adding um, these little masses that are shown right here until it balanced out, and then you know how much mass or what the weight was. So many of the mechanical balances, this shows like one that we would have in the lab, and such as the double pan balances have been replaced by digital scales and can definitely typically measure mass of an object more precisely. So as I said, we're going to use mainly the meter, kilogram, and second. And in English units, there is the foot, the slug, and the second. So mass in the English units are measured in slugs. But we can make conversions between these two. 1 foot is about 0.3048 meters. They figure a meter is a little less than a yard, and 1 meter is 3.281 feet. I'm sorry, meter is a little more than a yard. So we also have one slug is 14.59 kilograms, and 1 kilogram is equal to 0.07 about slugs. So we will need to talk about the difference between mass, which is a scalar, and it's a unit for mass are the kilograms and slugs, and weight, which is actually a vector, and it's a force. So the units for weights are in newtons and pounds. We often have to use, like I said, there's huge differences in the distances and times we have to measure in physics. So we use these prefixes, such as iota, zeta, exa, peta, and a couple of them might look familiar to you. For instance, there's the centi, which is for centimeters, and kilo, which is for kilometers, right? And you might know that a kilometer is 1,000 meters, and you might know that a centimeter is 1/100th of a meter. A lot of these I haven't used very often. In fact, a couple of them I've never used. The ones that are most common are kilo for kilometer and kilogram, centi and milli and micro, or centimeters, micrometers, and millimeters, and centiseconds and milliseconds and microseconds. So what these prefixes mean is, for instance, a kilo is 1,000. So 1 kilogram is equal to 1,000 grams, or we could write it as 1 times 10 to the 3 grams. Length, such as 1 centimeter, is 1/100th of a meter, and we can write it as 1 times 10 to the negative 2 meters, or 0.101 meters. We also have the kilometer, which is 1,000 meters, and we have the microsecond. This little symbol here is a lowercase Greek letter mu, and it's equal to 1 times 10 to the minus 6 of a second, so 1/millionth of a second. We need to make conversions a lot, and you've been doing this all your life in your head, but we're gonna formalize it so we can make it so that you can do it with any kinds of units. So, for instance, if somebody asked you how many quarters are in $3.50, you'd probably say 14 because every quarter, every dollar had 4 quarters. So that's 3 times 4 is 12. And then half a dollar would have 2 quarters. So it'd be 14. What you did in your head was you said 4 quarters equal $1. And let's divide both sides by $1. So $1 on $1 equals 1, which means this should still equal 1. So this is called our conversion factor. So if we have $3.5 and there's 4 quarters for a dollar, you get 14 quarters. So here's some other useful conversions. So 1 mile is 1,609 meters or 1.609 kilometers. And 1 kilometer is about 0.621 miles. An hour is 3,600 seconds, right? And there's 60 minutes in an hour and 60 seconds in a minute. So that's where the 3,600 comes from. In case you ever wondered, 1 year is equal to 3.156 times 10 to the 7 seconds. You can make a conversion of between kilograms and slugs, but to be honest, I've never known anyone who used the unit slug, so it's probably not necessary. We have 1 pound equals 4.448 newtons, and a pound and a newton and newtons are measured of forces, and it's the amount of force that the gravitational field of the Earth is pulling us down. So once again, if I need a conversion factor, I could take 1 mile equals 1,609 kilometers and divide both sides by 1,609 kilometers. That equals 1. So 1 mile divided by 1.609 kilometers also equals a mile. And we could do the same thing if we divide both sides by miles. So, for instance, we have 5 kilometers. Well, 5 kilometers, probably if you're a runner, you know that's about 3-something miles, right? So it's 5 kilometers, and 1 mile is equal to 1,609 kilometers, and we end up with 3.11 miles. And notice the kilometers cancel out. Is 20 meters per second fast? I'm not really sure. I'm used to miles per hour. So let's see. We know that 1 mile is 1,609 meters, and we know 3,600 seconds is 1 hour. So the seconds will cancel out and the meters will cancel out. And if we multiply 20 times 3,600 divided by 1,609, we end up with almost 45 miles per hour. So 20 meters per second is about 45 miles per hour. So that means 40 meters per second must be about 90 miles an hour, right? So 45 plus times 2. If we wanted to convert in the other way, so we had 60 miles per hour, we want to find out how many meters per second. We know there's 1,609 meters in a mile, and 1 hour is 3,600 seconds, and we end up with about almost 27 meters per second. If things are cubed, so for instance, let's say we look at a chunk of the atmosphere, and let's say it's 3 meters cubed. I'm sorry, 3 miles cubed. If we wanted to make the conversion, we would have to take the conversion factor and also cube it. So for each mile, we would need a conversion factor. And in case you haven't had a lot of math for a while, what this means is multiply 1609 times 1609 times 1609. So do it 3 times. So as we said, there's things called scalars and vectors. Scalars have magnitude only. So magnitude and so examples are mass and distance and speed. So for example, if you asked somebody directions to somewhere and they said it's 5 miles away, they're just telling you a scalar and it doesn't actually get you to the place. However, they say go 5 miles north and you'll know how to get there. So examples of scalars are mass and distance and speed. When people talk about velocity, they're talking about a speed in a direction. So maybe you're going 60 miles an hour east towards Atlantic City. Vectors are usually shown with little arrows over the top to show that they have this direction. So two examples, an example of a scalar and a vector is distance is a scalar. And it's the magnitude of the total distance scale traveled. Displacement is a vector. It's the distance between your final position and initial position, and it points in the direction from your initial position to your final position. So for example, let's say we have 43 miles per hour and we need to convert it to meters per second. First, we need to get rid of the miles. So we'll times it by 1609. Then we need to get rid of the hours, and we'll multiply it by 3600. I'm sorry, divide it by 3600. So we get 43 miles per hour, 1609 meters in a mile. The miles will cancel out, and 1 hour is 3600 seconds. The seconds will cancel out. We end up with about 19.22 meters per second. If you went in the other way, we would go 60 meters per second. We'd have to put the meters in the denominator so they cancel out, and the seconds in the numerator so the seconds cancel out. So 60 meters per second is about 134 miles per hour. If it was meters per second squared, so this is called an acceleration, we'd also have to square the seconds here. So we get 6 times 3600 times 3600 divided by 1609. And if we had 12 inches cubed, we'd need to cube that conversion factor. By the way, we could, don't forget, 100 centimeters is a meter, so we could actually, but we can't just move this over 4 times because don't forget, this is in centimeters, so it doesn't equal 1.964664 meters cubed. So if we were going to convert that to meters, we'd need to divide it 3 times by 100 meters. So what is mass? Mass is a property of a physical body and a measure to its resistance to acceleration when a net force is applied. What acceleration means is a change in speed or velocity, really. So what happens is if we apply a force, something could speed up or slow down depending on how the force is applied. But for the same force, a bigger mass will accelerate less. Its speed will pick up less. So for instance, if you ever had If your friend had a really small car and you needed to push it for some reason, you could probably get a couple people together and push the car. But if your friend had a tractor, trailer, truck, it would be harder to get it to the same number of people couldn't get that truck to accelerate, to start to move. Weight is just the force exerted on the mass of a body by a gravitational field. So the force exerted on a mass when it's near a large body, such as a star or planet. The bigger, more massive the planet or star, the greater the force. So weight is a measure of mass times gravity. So G is the acceleration due to gravity. So if I drop something on the Earth, it would pick up speed at 9.8 meters per second. So every second, it'll go about 10 meters per second faster. On the moon, the acceleration is much less because the moon is much smaller and has a smaller gravitational field. And on the sun, it's huge because the sun is much larger than the Earth. And the acceleration due to gravity is about 274 meters per second. So about 27 times the acceleration on Earth. So for example, here's an apple. Let's say it's about here's an apple. Let's say it's about 1/10 of a kilogram, right? So on Earth, it weighs 0.98 newtons. It's its mass times the acceleration due to gravity. On the moon, its mass would be the same, but the acceleration due to gravity is different. So it'll be about 0.163. And on the sun, it would be about 27 newtons. So about 27 times the weight as it would be on the Earth. But its mass remains the same. And if you're a person, you're probably about 60 kilograms, somewhere around there. So your weight on Earth is 60 times 9.8 or 5.88. On the moon, it would be 60 times 1.63. So you'd weigh about a sixth of what you would on the Earth. And once again, on the sun, you'd weigh about 27 times what you'd weigh on the Earth. There's a bit of confusion because in metric units, we measure kilograms and grams, which is a measure of a mass. But in English units, we usually use pounds and ounces, which is a force. However, the first is a mass, the second is a weight. We still write this down and say 1 kilogram is equal to 220 pounds. What they're really doing is saying, if you take the kilogram and change it to a weight, it's equal to the pounds. Or if you take the weight and divide 9.8, that's what we get. So don't forget, this is really a mass and this is a weight. And there's arguments about which one you should use, whether you should use the mass or the weight. But we'll stick with whatever the scale says, right? So if you're in metric, we'll use mass. And if you're in English, we'll use weight. Here's some common volume conversions that we use in cooking. So for instance, 15 milliliters is equal to 1 tablespoon or 3 teaspoons. So don't forget, a teaspoon is about 1/3 of a tablespoon. And 60 millimeters is about 1/4 cup, about 4 tablespoons. 1 cup is 8 fluid ounces. So there's another confusion. We have ounces, that's a weight, and ounces, that's a volume. Then we have 500 milliliters, which is 2 cups or 1 pint. Excuse me. And we have 1 quart is 2 pints, and 1 gallon is 4 quarts. So here's some common things you might see, right? So 1 ounce is 2 tablespoons. 1 pint, as we said, is 2 cups. And here's the conversion to milliliters. We also have 1 pound is about 0.45 kilograms, and 1 gram is about 0.035 ounces. If you think about it, gram is pretty small. Once again, these are ounces in weight. And normally, when you see this written, it'll say 1 cup, 8 fluid ounces. So there's no confusion. No, I don't want to add text. So let's say we have a recipe calls for 8 cups of cream, and you know it only sells by, you can only buy it in quarts, and you know there's 4 cups to a quart. So 8 cups divided by 4 cups equals 2 quarts. And how many cups in 3 gallons? So let's say you have 3 gallons and you need to know how many cups there are. We know that there's 4 quarts in a gallon and 4 cups per quart. So there's 48 cups in a gallon. Let's say we have 10 pounds of sugar. Well, 10 pounds, 1 pound is equal to 0.45 kilograms. So it's 10 times 0.45 kilograms or 4.5 kilograms. We also want to talk a little bit about density. And density is a measure of the mass per volume. So for example, if you look at sugar versus stevia, which is a liquid, which is a artificial sweetener, what happens is if we look at the mass per volume for each of those, if we looked for the same mass of each, the volume of the stevia would be much larger. So here's how we find density. We take the mass and divide it by the volume. In this case, our volume is 0.6, 0.3, 0.3. So our volume is length times width times height, or 0.0454 meters cubed. And our density is mass per volume. That's 20 kilograms divided by 0.054 meters cubed. And we end up with the density. So for example, let's say our weight is 1.96 newtons. So we've weighed this half a cup of milk, and the mass is equal to 0.2 kilograms. And I'm sorry, it's a cup of milk if you read the label. So we have 1 cup is 250 milliliters, and 1 meter cubed is 1 times 10 to the 6 milliliters. So we can find the volume. And now if we want the density, we just divide, sorry, we just divide the mass by the volume, and we end up with about 800 kilograms per meter cubed. The density of water is about 1,000 kilograms per meter cubed. So we'll end with this joke. Young boy is doing some cooking, and he's a science student, and he says the recipe calls for half a teaspoon of baking soda. That's 2.5 centimeters cubed. This is a 1 pound box. That's 2 times 3.5 times 4.26 inches, with about an inch of air at the top, which gives a density of about 2 point of about 0.0394 pounds per inches cubed. So I need about 2.7265 grams of baking soda. Then he calls to his mom and asks her for if she has a precision metric scale. And her mom says, "Why don't you just use half a teaspoon measure instead?" And the young boy says, "Where's the fun in that?" Anyway, I hope this has helped explain units and density and mass and weight, and I will talk to you soon.